Hi everyone. Thanks for the introduction. As Amit mentioned, my topic is about Hive and Spark. And first I'm going to go over some of the motivations why we want to do Hive and Spark. Then follow that up with some design discussions about challenges we face while doing the project. And last, if we have time, I want to actually do some demos, like run some queries on Hive and Spark. So let's get started. So first, a show of hands, how many people have actually used Hive before? Wow, it's like more than I imagined. So Hive is a very popular data query and management tool. And the reason it's so popular is that the language it exposes is based on SQL, which a lot of people know already. Right? So this thing is it's kind of like a tool on top of your distributed data set so people can use SQL to manage and query their data. The roots of Hive go way back. It goes all the way back to 2007 when Facebook started Hive. And at the time, so that was good and bad. So it was good because the Hive was like the front runner, but then it's bad because the technology that they use is limited by that time. So at that time, the only technology that was available was called MapReduce, which I'm sure everyone knows, right? This is like the most famous distributed processing engine in the Hadoop ecosystem. So if you know about MapReduce, you know that MapReduce can solve any kind of problem, but it won't do it very efficiently. So the problem with it is that it exposes only very simplistic primitives, one mapper and one reducer. And there's an implication that between the mapper and the reducer, what you have is a shuffle sort phase where the mapper keys are aggregated and then sent to the appropriate reducer. So translating some language like SQL, which is very expressive. SQL, you can do any kinds of joins and filtering and aggregation, any order. Translating that into MapReduce causes a lot of inefficiency. So the number one thing people say about Hive is, why is it so slow? Right? So imagine you have one Hive query, then it translates to, let's say, n MapReduce jobs. And each job is chained to each other, like a data pipeline. So the problem is, one, between map and reduces, you have to have disk I/O. Right? The reducer is assuming that the reducer output is going to go to disk, so the next mapper has to read it back from disk. So this is really wasteful, right? The more complex your queries, the more stages you're going to have, the more unnecessary disk I/O you're going to have. The second thing is, the main power of MapReduce is the shuffle sort phase, right? Where you shuffle data from the map to the reducer. And while this is good for some scenarios in your data pipeline, maybe you don't care about sorting. Maybe your query has no order by clause and you just want to get some data, but MapReduce is going to still shuffle sort at each phase. So due to the limitations of framework, Hive is not as performant as it would be. So let's see what people did to try to address that issue. So the first thing that people did, so people have been thinking about this problem for a long time. It's a well-known problem. So the first thing people did in 2013 was the community got together and for the first time tried to do an alternate backend for Hive called Taze. And this, I think, was a really good project. It was a good first step because what the Taze programming paradigm has that is superior to MapReduce is that you can, instead of just expressing your job as a mapper and a reducer, you can express it in a very free-form DAG, directed acyclic graph of execution. So in this example, there's different vertices connected by edges. So here you can kind of get more optimized physical execution for your Hive query. Because, for example, you can connect reducers directly to each other. There's no need to read the data back, having a dummy mapper just to read it back, just so you can get the next reduce stage. And if you don't want sorting, that's also fine. You can turn off, like for any particular edge, you can turn off the sorting for that edge. So here was a really good first step, I think, towards making Hive much more efficient. So why are we doing Hive on Spark now? So let me first take a step back and explain what is Spark. So Spark is like a new, really popular engine designed in 2011 by UC Berkeley Amp Labs. And we've been keeping our eye on Spark for a long time. And I think Spark in these recent years has really caught fire. And there's many reasons why Spark is so popular. So one was a self-perpetuating reason. One is that it has a really big user community, really big developer community. And the second reason is it's really easy to use. So I'll talk about these two and why we ended up choosing Spark as our execution engine. So one of the main advantages of Apache Spark is that it has a community. So people, if you know open source, you know that to have a really strong open source tool, you need a big community around it. So I got these numbers from the Spark Summit that was held earlier this year. So it's already the most active project, surprisingly, in the Hadoop ecosystem. In June 2014, there were already 255 contributors from 50 companies. And there were, in that 6-month period, there were already 1,200 commits and 250,000 lines of code change. So that explains that Spark is evolving at an incredible rate. And the user community is also very strong, as evidenced by the fact that many Hadoop tools across the ecosystem, such as Pig, Flume, Mahout, Crunch, Solar, and a bunch of other ones not listed here, are moving on to Spark as an alternate processing engine. Right? So Hive fits that mold really well. And kind of the reason why it's so popular is that it has a really nice programming paradigm called RDD. So RDD stands for Resilient Distributed Data Set. So when you first read about it, it doesn't seem like the dictionary definition is just a fault-tolerant data set. But when you actually look at it, what I think of it as is like a stage in your data pipeline. An RDD is something that represents distributed data at any point in time. So you create it. Let's say you first create it from an HDFS file, which is a distributed data. The way you get other RDDs from this RDD is you do something called a transformation. So RDDs are read-only. The only way to get from one RDD to another is doing a transformation. And I think it's the transformation and the actions of the RDD that make it really powerful, because out of the box, there's already dozens of transformations that you can call on your RDD. So if you remember, MapReduce only had 2. Right here, you have map, filter by, group by, all sorts of things where you can also plug in your custom code, custom functions. It's very expressive to exactly specify what you want to happen in your cluster. And also, there's different actions you can take, like you can say when you want this RDD to spill to disk, when you want to cache in memory. So we have really fine-grained control for the first time to do efficient representation of a Hive query on a distributed system. So this is really exciting for us. So that brings us now to the collision of these 2 projects, which is called Hive on Spark. So people have been thinking about Hive on Spark for a long time, actually. So the first time that they thought about it was that when Spark first came out, I think the AmpLabs people, the same people who made Spark, came up with a project called Shark, which was a proof of concept saying, we can actually run Hive on Spark. So what they did is they forked Hive, and they kind of ripped out the internals, and then they put Spark into it. So this was good to show us that it could happen really easily, but the problem is that Shark wasn't really well maintained by the Hive community. It was done outside the Hive community in a separate GitHub project. So obviously as Hive continued to evolve, like Hive 10, 12, or 11, 12, 13, 14, it became increasingly hard, if not impossible, to port changes back to Shark. So that's why in 2014, in Spark Summit, Databricks announced that the Shark project was sunsetted. So that's where we came in. So that's why we took some of the lessons of Shark and are now doing Hive on Spark. So what we're doing differently is we're doing it within the Hive community. So a lot of committers and contributors within the Hive community are working on this project, and that will ensure that future versions of Hive 14, 15, 16, are all going to have Hive on Spark. And we're also doing it code-wise. We're doing it in an architecturally compatible way with the rest of the Hive code base. So we're going to keep the exact same physical abstraction for the physical layer and the logical layer, so that Taze and Spark and MapReduce all share the same physical kind of code APIs, right? So this helps us both for code maintenance, right, having a clean API, and also maximizes reuse of common functionality across the Hive code outside the physical layer. And the point of this project, I want to kind of take a detour, like what this is going to entail for the users. So Hive already has a huge user base, as kind of you've seen here, and what they're going to get from their great investments in Hive is that they get another option of execution that you can turn on with just a few flags. So with just like 1 or 2 flags, you can switch between MR, Taze, or Spark. And as Spark becomes more popular, so Spark, as we're seeing, becoming very popular in stuff like not only the stuff I talked about earlier, but also for machine learning, graph processing, streaming, a lot of our customers are actually starting to play around with Spark, starting to invest in Spark clusters. And when we tell them that, hey, you can also run your existing Hive jobs also on Spark, it's really great for them because they can consolidate all the investments on the Spark cluster, consolidate all the expertise. Right? And as the Spark has a very strong community, this will let them have continued improvements of Spark over time, right? As Spark continues to evolve. Yeah, so that's at like a motivation level. Now I'm going to get into some of the nitty details of the anatomy of Hive and how we plug Spark into it. So this is kind of like anatomy 101 of Hive, like what happens inside Hive. So Hive, as I mentioned before, takes a query, and then it goes through a process called semantic analysis to create an operator tree, which is something that is just objects that say what has to be done, right? And then from the logical operator tree, it goes through a second process called task compilation into a physical task. And this is something that you can send into your cluster to run. So this abstraction that we chose is at three places. One is the task compiler, the task, and the work. Work, there are some like things inside the task that send into the cluster to run. So basically, when we abstract out at this layer, we can have like different compilers create different tasks for their systems to run. And this keeps the rest of the code very clean. Stuff that we keep by doing it at this layer, like all this stuff is common across the different execution engines. For example, all HQL, all the Hive query language is supported by default, even though it's Spark or Taze or MapReduce, because it happens at a higher layer. Similarly, all the integrations of existing tools like plugins, people have drivers, authorization, user-defined functions, UDFs, storage handlers, everything is also kept because it has nothing to do with this layer. And also, some people might not realize, but even logical optimizations. So sometimes you don't even need to know what cluster you're running in, and you can do some optimizations. Like I want to push down, do predicate push down. I want to reorder my join. I want to do some logical stuff, and that all happens at a higher layer. So this is what makes this abstraction really nice, I think, for our users. So I'm gonna do two examples before I start my demo. And these two examples are going to kind of show in greater detail what exactly happens on Hive on Spark versus Hive on MapReduce. So first, Hive query, this is a sample query that I wrote. So this query is kind of a simple query. It's just SQL, so people know SQL is just a filter, and then there's an aggregation after that. So in this query, it creates a kind of a simple operator tree. Right? Operator tree is nothing but a set of steps, what has to happen. So it first has to scan the table, then do a filter, do a projection, and then do an aggregation, which is the group by, followed by the final projection for the result. So in the MapReduce world, what happens is the MapReduce compiler looks through this and says, it narrows in on the group by. It says group by is great because MapReduce framework is built for that, right? MapReduce framework will aggregate keys of the mapper to the reducer, which is exactly what group by does. So in a MapReduce work, what it looks like is it takes the first part of the operator tree and then it puts it into the mapper. And then it takes the second part of the operator tree and puts it into the reducer. So in between, there's a shuffle sorting phase, right? Where the MapReduce framework takes the keys of the mapper and shuffles them to the reducer. That's what actually achieves the group by, right? So this is great, but except for one thing. It also does sorting that we don't actually care about in this particular query. So how is Spark any different? So in Spark, what we can end up doing is we can make a more intelligent choice because the Spark API is much more expressive. We can tell Spark cluster, hey, in the middle phase, we actually don't care about sorting. We just want to run a group by transformation, right? So we kept most of the logic almost the same. If you see the previous one and this one, the two operator trees that were broken up, they're still there. But it's just that in the middle, by changing the shuffle sort to a group by, we already achieved much greater savings. Right? Now, I want to go into a little more complex query. This is a join. So in this join, I have two source tables that I'm trying to join together. And I apologize if the font's a little small. But these two tables also have a filter clause. Then I join them, and then after I do the join, the whole thing I'm doing an order by clause. So the operator tree is kind of similar, except there's obviously two source operator trees, and they feed into one join operator. And then after the join operator, there's a select operator, a sort operator, and then a final select operator. So again, what MapReduce does is it goes through this operator tree and identifies places that it can fit in the MapReduce boundary. So join is a perfect example, right? So what is a join? Join is nothing but you have two tables and you want the same keys to flow to the result, right? So that's what MapReduce does too. It takes two tables and then the same keys will flow to the same reducer. So that's the one MapReduce boundary. The second MapReduce boundary is at the sorting, right? Because how do you do sort in MapReduce? Well, again, you have to do shuffle sort. That's the only way really you can do. So what you end up with is kind of a very wasteful MapReduce structure where you have actually two MapReduce jobs. So the first MapReduce job takes care of the join. The second one takes care of the sorting. But in between, you have to spill to disk and read it back again. So this is entirely useless mapper right there. All it does is read back from disk, just so you can get the second reduce, the second shuffle sort. So what we can do in Spark, again, we can do a much more optimized way to handle this query. We know exactly what we want. And so instead of spilling to disk, what we can do is actually directly feed the input of the second reducer, or sorry, the first reducer to the second reducer. And we don't need the phantom mapper anymore, right? So I just go back real quick. There was a useless mapper here, so we got rid of that by just directly connecting the output to the second reducer. So this expresses the exact same thing, but because the language allows us to express it much more efficiently, we get some performance improvements from that. Okay, so I'm gonna, I think I have time to do a quick demo real quick. So in my demo, I'm going to kind of try to show you guys like how easy it is to get the same query running on MapReduce as well as Spark. So I'm going to start up Hive Server 2 with already the required dependencies required to run a Spark. And then I'm going to start Beeline. So Beeline is the JDBC client to Hive. Sorry, I'm going to type a little slow because I'm holding the microphone. So in my demo, I have three tables that I'm going to try to join together. Okay, and in Hive, so one thing to keep in mind is that in Hive, you don't actually need a cluster to do a select star. So I'm just going to show you the tables right now. So the first table is an item table where, so the first table is an item table. It's kind of like a fact table where I have items and I map them to products and stores. But it's only the IDs of the product and store. So I have those in the other dimension tables. So I have one that's products and one from store. So I have three tables all together, and I'm going to try to do a join of these. Again, this doesn't actually require the use of a cluster because this is just reading from a file. So I'm going to start up the Spark cluster, and I'm going to do it in a standalone mode. So this is good for demo, but in production, you probably want to do it on a resource manager. So Spark starts pretty fast in standalone mode. So I'm going to show you that the Spark master web UI is started, and this is the Spark master URL. So what I'm going to try to do now is to run one query, one join. So I don't know if people can see this, but this join is between product table and the item table. So two of my tables. And I'm going to do a group by and an order by. So kind of similar to the example I was showing a little earlier. Oh, I'm sorry. So, so one thing I need to do first is I actually need to set the execution mode to Spark, right? So all I need to do is set 5 flags. So let me just go through. So the main flag really is Hive execution engine is Spark. And the other flags is like where the Spark master lives and how much memory to give and so on and so forth. So I'm going to run the join query now. Oh, I'm sorry. So the first query sometimes takes a little longer because it has to do initialization of the Spark client. But as you can see, the query ran with the expected results. And if you look at the Spark master URL, you see one application running. This is the one that we just ran. Called Hive and Spark. And if you click into the application, you can see the logs. And you can see that this is actually running apologize for the resolution, but you can kind of see the Hive operator tree actually running inside this Spark cluster. So I'm going to do another query. Like this is a more complex query, a slightly more complex query. Basically, it's a three-way join between product, store, and item table. And the second one usually completes a little faster because the Spark client is already up and running, right? So this is exactly the result that I wanted. And to prove that, I can set this the execution, the cluster back to MapReduce, and run the same query. So yeah, so MapReduce has to do some so it has to do some file. So it has to do a lot of file I/O, but you can see it came with the exact same result, right? So this is from MapReduce, and this is from Spark. So we have a few basic queries running actually on Hive and Spark. So I'm going to go back to my presentation and just finish up, and then take questions. Yeah, so this slide, I'm just trying to explain that this project not only benefits the Hive community, it also benefits the Spark community, because we created a lot of, Hive as kind of like a very complex application. We have a lot of requirements that other applications might also have when trying to migrate from MapReduce to Spark. So for reduced site join, we had a requirement to do partition plus sorting, just like MapReduce did. So surprisingly, Spark didn't have that API, and we added that in Spark 2978. We have stuff like remote Spark context, so Spark context is the client, the Spark client that I was just showing earlier. So the Spark client, when we're trying to do multi-user testing, we found that it wasn't really concurrent. So we're going to have a project to push that down into the application master and make it more concurrent. And then of course there's stuff like monitoring APIs that we need to build, and then elastic scaling also, Spark application. So so I didn't get to show, but like in the demo, actually it's the same Spark application taking all the queries for the same user session. So we want that application to be able to increase and decrease resource usage from the resource manager as appropriate. So that's pretty much my whole the whole presentation. I wanted to thank contributors because no one company could do this alone. We have a large community helping us out. And we have one umbrella Jira, Hive 7292. So if you go to that Jira, there's like hundreds of subtasks that people are working on all the time. And you can follow our progress there. And thank you all for attending this presentation.
So did you do a performance comparison with Impala?
No, we're actually at a very early stage of Hive on Spark. We haven't done much performance optimizations. So yeah, a lot of people have asked us about Impala, so I'll just go ahead and answer that question. So Impala, the use case is really for BI and analytics. So Hive on Spark, we're targeting really existing Hive customers. We're trying to make it so that they can run existing Hive jobs on Hive on Spark. We're not really trying to be, it's not the goal of this project to be Impala performance. So the question is about Spark SQL. Have we compared the benchmark against Spark SQL? So again, this project is very early. I think Brock just did one comparison with MapReduce. So we haven't actually gotten that far yet. Spark SQL is also a very early project. I think they just announced it earlier this year. So we have to again wait and see what they're going to do. Yeah.
Have you tested it with HDFS flash sharing yet?
No, so again, this project is very early. We haven't really done that much testing. We just kind of started this a few months back, but definitely that's probably down the line.
Hey, very cool presentation. One question I had though is, it seemed like throughout the presentation you kept using Hive on MapReduce as a straw man to compare against Hive on Spark, where it seems like the actual interesting comparison is Hive on Tez versus Hive on Spark. So do you have anything to say about, Hive on Tez versus Hive on Spark?
Yeah, that's a good question. So I had one slide where I already kind of explained what Hive on Tez does. So Hive on Tez, Tez I think is also a great framework in terms of, it also offers the same power as Spark. But I think what Spark has going for it, why we chose Spark was the two reasons I listed. One, it has much more community, so we think that it's going to, over time, take over MapReduce. And the second reason is if you actually code in Spark, you'll realize that it's actually a lot easier to reason with the API. So Taze, while maybe the functionality is the same, Taze you have to, the API is more like you have to construct a DAG, a whole entire graph, whereas Spark, you can do it in just a few lines of like RD and transformation.
Okay, well, just as another point, I mean, though, people aren't going to be people who are writing Hive SQL queries aren't going to be, writing in Hive or in Spark. So to them, it doesn't really matter that much that Spark has a nice API.
So the first point was like the community. So I think in the long run, we're not trying to displace Taze at all with this project. So we're just trying to offer them another alternative. If people decide to go with Spark as the long run, I think it'll really make sense for them to consolidate that investment. That's the point of this project. Thank you.
All right, any other questions? All right, let's have a big round of applause for all of us.
Just